My name's Gail Atkinson, and I'm a professor at the University of Western Ontario. And this morning I'm going to be going over with you some recent updates in seismic hazard assessment for Canadian urban centres. And this is just a brief overview of my presentation. John's information, I think, leads very nicely into this. I'm going to talk a little bit about what our approach is for assessing hazard in Canadian cities, the input models that are used, and in particular, some of the things that are new in those models that are impacting how we view hazard in Canada, particularly in the urban centres. And these are new trends and new data in analyzing ground motions and the strength of ground shaking from earthquakes, and also looking at, in particular, what the impact of new information is on seismic hazard assessment and how that might play out in future both site-specific assessments or perhaps in future assessments for national building codes. And at the end, if there's a little bit of time, I might just touch briefly on the subject of time histories that engineers use for analyzing structures. But we'll play that by ear, see how the time goes. So first of all, the seismic hazard methodology. John already went over this, and so I won't belabor it in detail. I've just put up here a summary from the classic textbook example of a seismic hazard analysis. I don't want an automatic update. No, I don't want to restart the computer later. So I think I will just go like, just restart later. There we go. So this is the classic four-part seismic hazard analysis, and you can tell it comes from a textbook because you can kind of see the photocopy smudge marks there in the background. And as John reviewed, there's four basic steps here. We begin by identifying where we think the earthquakes happen, and we do that by defining seismic source zones, which might be either fault sources or aerial sources. And then for each one of those sources of earthquakes, and as John mentioned, there are sources of earthquakes everywhere. There's no place in the world where you can say, oh, there's no source of earthquakes here. It's just a question that some sources are a lot more active than others. So how do we describe how active those sources are? That's what we do in the second step, where we have a magnitude recurrence relation that tells us how often earthquakes happen in a source zone for different earthquake magnitude levels. Then in the third step, we have ground motion prediction or attenuation relationships that tell us how strong the shaking is as a function of magnitude and distance. And these are the things that are really important because we don't really care from the point of view of hazard how big the earthquake was. What we care is how strong are the ground motions. So people will say things like, oh, well, you know, could a structure here in Toronto survive how big of an earthquake could it survive? And I like to say, oh, well, you know, we had a magnitude 9 earthquake in March, but it was really far away. It was in Japan. So the motions here in Toronto weren't really very strong. And so we had no problem in Toronto surviving a magnitude 9 earthquake. So the magnitude of the earthquake by itself doesn't tell you anything about the ground motion. It's all about how close the earthquake is as well as the size of the earthquake to give you the overall strength. And that's what the ground motion equations are doing, is telling you how strong are the motions for earthquakes of different magnitudes and distance. And they're pretty much a key component in a seismic hazard analysis. So we combine those ground motion equations along with the magnitude recurrence data that tell us how often the earthquakes of different sizes happen, and the source zone information that tells us whereabouts those earthquakes happen. And we use a mathematical computation then to take all of that information and integrate it together to tell us what's the likelihood of getting different levels of strong ground shaking as a function of probability. The lower is the probability, or the less likely is the event, the stronger is going to be the shaking. For example, we know that it's very likely that here in Toronto, sometime in the next 50 years, we're going to get a level of shaking that's strong enough that people will feel it, or at least some people will feel it. And we also know, of course, that it's much less likely that we'll get a level of shaking here in Toronto that's strong enough that it will cause damage to structures. So as the intensity level goes up, the probability level goes down. So in a seismic hazard analysis, some things that have sort of changed, sometimes people say, well, why do we have to reassess the seismic hazard? Didn't we already do that some time ago? And yes, of course, we've been assessing seismic hazard for decades now. But as new information is gathered, our assessment of the hazard changes. The hazard itself doesn't change. The hazard is the same as it was 10 years ago. But our ability to assess the hazard changes, and so consequently what we might want to do with that information might also change. And so some of the things that are new is we continue to improve seismicity catalogs. As John mentioned, a decade goes by, we've got 10 years more of earthquake data. We also have a little bit better understanding of where the earthquakes happen. That has some impact on hazard assessment, but not a big impact. There are other technical factors that I don't want to go into in detail today that can make some impact, like how you treat different magnitude scales, some details of how you model earthquake sources. Those things can be important, but the most important thing, and what I'll sort of focus on a little bit more today, is new ground motion prediction equations. Those are the equations that tell you how strong the shaking will be as a function of magnitude and distance. And those change quite a lot over time, especially because with all of the recording equipment that we have out all over the world, we keep getting more and more data. And as our data grows, so does our understanding of what ground motion levels to expect. So some of the things that we've been looking at in the Canadian Seismic Research Network in terms of updating hazard assessments. One of them is coming up with a new seismicity catalog, and this has been a parallel exercise to the one that John described that's also going on at the Geological Survey. We've kind of updated seismicity catalogs to take into account new events and to better combine different data sources from Canada and the US, and to better look at converting magnitude scales so that we look at all of the events in the same way. And we have a website that I've put here in the presentation, seismotoolbox.ca, where a lot of our actual technical products are available for other people in the network and indeed other users across Canada to use if they would like. And this is just an example from our of the data in our website, showing the catalog that we've compiled for Eastern Canada, where here the red dots are earthquakes bigger than magnitude 6, and then the dots get smaller as the earthquakes get smaller. Very similar to the plots that John showed. And similarly for Western Canada. And you can see even at a glance that there's more earthquakes in the west than there are in the east, but there's earthquakes in both places. And you're kind of pretty hard-pressed to find much of an area when you look at maps like this where you can say, oh, there aren't any earthquakes at all. You know, they're sort of scattered about, but you get small earthquakes pretty much everywhere. So we use this seismicity information along with new information on interpreting why earthquakes happen and where they've happened in the geologic past to come up with new source models to describe the hazard. And I'm not going to go into this in detail here. We have a paper that we published in the Bulletin of the Seismological Society of America that kind of presents our new interpretation of the sources in Eastern Canada in terms of what we think might be going on with rates. And John also talked a little bit about this in his presentation, where we think we're starting to get a little bit better understanding of the relative rates of small and large earthquakes in different parts of Eastern Canada and how they behave. And we use different ways to characterize these features. The magnitude recurrence relationships that I mentioned that describe how often earthquakes happen of different sizes. We've looked at these in sort of in more detail and in new ways in the East to try and get a better handle on not only what the rates are for smaller earthquakes, but what we think the rates might be for larger earthquakes using various lines of geologic evidence that are kind of based on information that is in the sort of the post-glacial soil record, or the soil record for the last 10,000 years since the last glacier retreated. In parts of eastern Canada, we can look at the soil deposit and see from the soil record whether it appears that there have been large earthquakes in a particular area or near a particular area in the post-glacial period or not. And this helps us to kind of constrain some of these relationships between how often earthquakes happen at big magnitudes and get a little bit better handle on uncertainty in the rates of large magnitude earthquakes. So we've tried to build some of these technical features into new assessments of hazard in the east. And then, as I mentioned earlier, one of the biggest changes in seismic hazard assessment has been in ground motion prediction equations. And there's been a lot of work in this field over the last decade or so. And so in our assessments, we use different alternative relationships that have been published within the last 5 to 10 years to characterize what we think the average levels are for different ground motion parameters like acceleration or velocity or response spectra, which I'll talk about in a minute. Because different investigators use different databases and different techniques in coming up with these equations, you'll find more than one of them in the literature. So one of the sort of classic ways that's used in a seismic hazard assessment to look at the impact of these alternatives is to basically run an analysis multiple times for multiple different possible ground motion prediction equations and analyze the differences in results to come up with estimates of uncertainty. And so this is just a sort of a little slide that shows peak ground acceleration as a function of distance for a particular earthquake magnitude. On the left, it's the accelerations that are expected for shallow crustal earthquakes of magnitude 7 in eastern Canada. And on the right is just shown an example for events that happen in the subducting slab beneath British Columbia for earthquakes of magnitude 7.5 in the west. And just to show that different investigators, as shown by the different colored lines, will predict a different median equation, and that will impact hazard estimate. So when we look at how all of those factors play out in an estimate of seismic hazard that we made last year as compared to ones that were made about 10 years ago for what's in the building code at present, we get a picture that looks something like this in Montreal and Ottawa, where what's shown by the dots are what's currently in the National Building Code as the seismic sort of design parameter, as if you will, for Montreal and Ottawa. And so what this graph is showing is the amplitude of the ground motion that a structure would be designed for as a function of the natural period of vibration of the building. So if you have a short rise building, say something that's only 1 or 2 stories, it would have a short period, something like about 0.2 seconds. And so you would pick one amplitude level. I don't know if this mouse will work. So if you had a short rise building, you'd be looking at an amplitude in this range. And if you had a high rise building, it would have a longer period, and you might be looking at an amplitude in this range. And so at present, we have amplitude levels in the building code in Montreal and Ottawa that are sort of represented by these dots. And when we do newer analyses with some of these new factors, we find that things could potentially change significantly. The red line is our new estimate for Montreal, which is not too much different. The blue line is our new estimate for Ottawa, which comes down quite a lot because of new ways of treating the seismic source zones and how we think the long-term seismic behavior is. So, so far, and it's sort of things are still in a state of evaluation at the moment. We don't know what will be the final answers or provisions for the next round of the building code, but we think that overall, potentially, we might be looking at least in some locations in the east, lower estimated hazard for some cities. In Vancouver, based on our analysis last year, this is what we came up with, where again the red dots are what's currently in the building code for Vancouver, and the red line is what we calculated with our newer model. And in this case, we think that possibly the seismic hazard estimate that we now get for Vancouver might be a little higher than what we got before, partly because, as John mentioned, in the current round of building code calculations for Vancouver, we didn't include the hazard from the Cascadia subduction source on top of the hazard from the crustal and the in-slab events. We considered it sort of as an either-or menu, where if we look at what the overall implications are for hazard, the fact that there's more than one source means that the hazard is actually a little bit greater than what we had calculated. So just looking at where this hazard would come from, we can deaggregate the hazard analyses to look at the contributions to the hazard as a function of magnitude and distance to get just some idea of what are the sources. And here this is all based on the 2% and 50-year probability level. I should have mentioned that earlier, which is the same as what's in the current building code. And if we look at Montreal, we look at 2% in 50 years, most of the hazard is coming from the likelihood of getting earthquakes of, say, in the range from magnitude 5.5 to 6.5, happening at relatively close distances, less than 50 kilometers. So we're not looking at a giant earthquake. What we're looking at is if we happen to have the misfortune of having one of the moderate size earthquakes that can happen in the east happen close to Montreal as opposed to further away from Montreal. So something like a magnitude 6 earthquake happening within 20, 30 kilometers of the city, say, it's not that giant an earthquake, but that's the kind of scenario that gives us 2% and 50-year ground motion levels in Montreal. In Vancouver, one of our main sources of hazard is that the in-slab motions, is the possibility of in-slab earthquakes of about magnitude 7 happening beneath the city. That's at depths of about 50 kilometers. And because it's at a depth of 50 kilometers, that's why you see this sort of bulge in the hazard deaggregation at distances of around 50 kilometers. That's really a depth in that case of 50 kilometers. And this is a short period hazard that I'm looking at here because it's a peak ground acceleration, which is dominated by events that happen nearby and that have high frequency content. So when we look at something like peak ground acceleration, we don't see a big contribution from that large Cascadia earthquake. There's that magnitude 9 earthquake that John told you about on the Cascadia subduction zone, about 100 kilometers or so, 100 plus kilometers from Vancouver. And it doesn't look very important in a plot like this, but the thing to keep in mind is that if you look at the hazard for longer period structures like high rises, where you might be interested in not peak ground acceleration, but something like the response at 1 second or 2 seconds, then the hazard contributions could look quite different. And in fact, then the Cascadia event would look a lot more important. So I'd like to show you a little bit about how we can use sort of some of the ground motion information to look at what those scenario motions might actually do if you were in a city. And the first plot I'd like to show is a scenario shake map, this is called. And what a scenario shake map is a map that shows the intensity of shaking for some postulated event. And in this case, our scenario is a magnitude 6 earthquake happening about 15 or 20 kilometers away from the city of Ottawa. In this case, we have just arbitrarily placed it north of the city, which would put it somewhere in Gatineau. No reason for that other than you have to put the earthquake somewhere. And so that there's no need to evacuate Gatineau at this point. We're just doing this as an exercise to say, well, if you had an earthquake like the Val de Bois earthquake, but say it was bigger, a magnitude 6 rather than a magnitude 5, and say it was closer to Ottawa, 15 or 20 kilometers rather than 60 kilometers, what would the ground motions likely look like? The other reason we put it at that magnitude and distance is because it just so happens that if you do that, you get motions that are very close to the 2% and 50-year motions that are in the building code for Ottawa. So if we actually got those motions that we're designing buildings for today, what kind of damage pattern might we expect to see in Ottawa? And this is the result. And this takes into account the expected ground motions and also how they're amplified by the local soils. And later today, Dariusz is going to be telling you about how microzonation studies have been done to tell us what those soil conditions are and how they would amplify ground motions. So we use that information in these in making these maps. And this shows the predicted intensity across the city of Ottawa. And the red area is sort of the area of maximum intensity. And in this case, that would be in the Orleans area, which is the eastern part of Ottawa. And as Dariusz will tell you this afternoon, that's an area where there's a lot of deep, soft soils, which tend to amplify ground motions. That's why the motions are the highest there. And in other parts of Ottawa, where the soils are more competent and or maybe they're a little further away from the epicenter, the intensities might be significantly lower, say around intensity 5 or so. And just to sort of give you a handle, that maximum intensity of 7 is the kind of intensity that would cause negligible damage in a building that had good design and construction. In other words, if it was one of those buildings that we actually did design to what's in the building code, you wouldn't see any damage or not significant damage. But in poor structures, you could get considerable damage. It should also be kept in mind that this is just an overview level of map showing an average predicted intensity. We know that in real situations, intensity can vary quite a bit just from one block to the next or even over shorter distances, so that in some cases, in some areas, intensities could be higher and in some it could be lower. It's just an overall average. This is a similar map for the Fraser Delta area of Vancouver, where I know you may not look at this map and instantly recognize Vancouver. So there's a couple of labels on there, the airport in Richmond and then downtown Vancouver on the north side of the map there in green. And this is an approximation of the intensities that we would expect due to ground motions from a magnitude 9 Cascadia earthquake happening about 150 kilometers offshore, just one scenario, and some of the sort of typical amplifications expected for the kind of sites that you get in the Fraser Delta. And the group at UBC is doing a lot more detailed work on the seismic microzonation in BC, in the Richmond area, and other areas in North Vancouver and so on, and there'll be a lot more work coming out on details of shaking and amplification from this work in the near future. And so in this case then, for that particular scenario, the maximum intensities would be somewhere perhaps about 8 on average, which would be the type of ground motion that might cause only slight damage if you had properly designed structures, but could cause quite considerable damage in substandard buildings. So when you look at shake maps like this, it kind of, in the intensity level, it kind of gives you an idea of what types of damage that you might expect. And again, it kind of also brings the message that if the building was designed for a modern building code, it's probably going to perform relatively well, but there could be quite a lot of damage to the structures that have neither been designed nor retrofitted. So I want to talk a little bit more about ground motion prediction equations. How am I doing on time, Dennis? I didn't look when I started. So about how much?
We've got about 10 more minutes.
Okay. On ground motion prediction equations, I'll just talk a little bit more about these. These are a key input to the seismic hazard models, as I mentioned earlier, and they also drive output ground motion maps for things like scenario shake maps. So these are those equations that describe shaking intensity as a function of the earthquake magnitude, the distance, and the site conditions. And these equations are influenced to a very large degree by the database that we have of recorded ground motions. And this database has increased 100, perhaps even 1,000-fold in the last decade or two since we last revised the building code maps. And these newer ground motions have been used quite routinely in site-specific analyses and are now being addressed for future building code revisions. So one of the key differences in ground motions that's important is the difference between the ground motion strength in the east versus in the west. And this graph is showing for short period motions on the left and long period motions on the right what are the typical differences between ground motions that we deduce from these equations in eastern Canada and in western Canada, where the west is the dashed black line and the east is the solid blue line, and the motions that are expected for a reference firm site condition for magnitudes 5, 6, and 7.5 are shown by the three curves. And the sort of overall message from this is that if you're looking at long period motions and you're sort of within the first 100 kilometers or so, those motions might be relatively similar. But then as you move out to larger distances, you're going to see that the motions from the east are sort of higher and higher relative to those in the west. And if you look at short period motions, those motions in the east for the same magnitude are higher than the ones in the west at all distances. And by the time you get out to hundreds of kilometers, 200-300 kilometers, the motions in the east for the same magnitude can be higher than those for the west by an order of magnitude, a factor of 10. And that's just due to the fact, well, not only because they started stronger, because the east can generate more high-frequency content in the earthquakes to begin with because of the sort of stronger, less frequently fractured crust. And for the same reason, those motions can propagate more efficiently to large distances, so that you tend to see, for an earthquake of the same size, a much, much larger felt area and also a larger damage area for an earthquake in the east. And this is an important factor because it tends to kind of level out, in some sense, hazard between the east and the west. And it's why the hazard in the east is significant, even though we don't get earthquakes as frequently as we do in the west. So just in very rough terms, you could think of it that in the west, the earthquakes might be happening 10 times as frequently, but when one does happen in the east, it might affect an area that's 10 times as big. So in a way, it kind of evens out in that sense, in a hazard sense. And there's different measures of ground motion that are used for engineering purposes, and I'm just going to describe them very briefly. Most people kind of understand what acceleration and velocity is because we do that every day in our cars. But most people don't have as an intuitive appreciation for what an engineering description of ground motion is, which is often an elastic response spectrum is a simple way of describing ground motions for engineering input, and it is in fact the most common output of a probabilistic seismic hazard analysis, and that's actually what the building code specifies, is what's the elastic response spectrum that you should be using. These things are also often used as a kind of a basis for specifying time histories or actual ground motions to use in a nonlinear analysis for engineering. So the reason that we use these other measures, in particular the reason why engineers like response spectra as compared to just an index like acceleration or velocity, is that it's a handy way of describing not just the amplitude of the motion, but also what its frequency content is. And that's important because the frequency content will have a big impact on how it affects different kinds of structures. And just as an example, this shows a plot of 4 different records of acceleration versus time, and they all have the same peak, 0.18 g, or 18% of the acceleration due to gravity. But you can see, looking at them, that they look really quite different, even though they have the same acceleration. And that's because they come from different magnitudes and different distances, so they have different durations and different frequency contents. You can see that a lot more clearly if you plot the response spectra of these records, which tells you, instead of just one peak amplitude, it tells you what the peak amplitude is in each different period range. And it's plotted on 2 scales here. I plot on a linear scale because that's what engineers really like, and I plot it on a log scale on the right because that's what seismologists really like. And believe it or not, those 4 lines are the same on both plots. They're just plotted in different scales to show different features. But the main point here is that you can see when you plot these motions in terms of their frequency content that they are very different, even though they all have the same acceleration. And in particular, the one that's plotted in red, which happens to be time history from a magnitude 8 earthquake in Mexico City, which had a very famous resonance peak at a period of about 2 seconds that brought down high-rises all over Mexico City. And you can see that feature when you look at a response spectra. You can't see it when you look at acceleration. So that's why we use these alternative measures to emphasize the frequency of the motion. And then when we look at characterizing seismic hazard, we tend to just connect the dots on a piece of paper that shows the amplitude as a function of period, where for a given probability level, what we're looking at, the uniform hazard spectrum, is just simply plotting at each different period what that maximum amplitude is, and then connecting them together so that we can see both the amplitude and the frequency content of the motions that we're expecting. How are we doing for time, Dennis?
We've got a couple of minutes.
Couple minutes. I'm thinking I want to skip some of this stuff because I think it's maybe a little bit dense. And I think I'm going to go with the last couple of minutes, talk about a couple of the things that we've learned from the Tohoku earthquake in Japan. I know I sort of apologize for skipping through a bunch of slides, but trust me, you didn't want to see them anyhow. They were like way too technical. I decided at the last minute that I would just slow down and describe the slides that I did show rather than try and show all of the slides. But I do want to show this one, because I know that the Tohoku earthquake that happened in March, the magnitude 9 in Japan, was a very interesting event to everyone in this room, as well as, of course, a tragic event for Japan. And the one good thing about this earthquake is that we are able to learn a lot about ground motion from it, and in particular about the kinds of ground motions that we might expect in Western Canada from future earthquakes like this off the coast of BC. So one of the things we've been doing in our research group is analyzing ground motions from this event. Japan has the best seismographic recording networks in the world, and so when an earthquake like that happens in Japan, we learn a lot. And these dots are basically, each dot represents a seismic recording station in Japan. And you can see that hundreds and hundreds of instruments recorded these motions at distances ranging from about 50 kilometers out to several hundred kilometers, which is really the entire distance range of interest. In Vancouver, Victoria, we're sitting at, you know, somewhere roughly in the 100-kilometer distance range from the subduction zone. So these motions are very important to us. And there's been various prediction equations that were made before the earthquake happened of on average, what such motions would look like. And one of the things that was of interest is to see, well, how did the ground motions for this event actually compare to those that we expect? And here in this plot, the black lines are prediction equations or regression equations that we developed just from the Tohoku earthquake data, so that just describe the average amplitudes of this earthquake for two types of stations, those that are in front of the line of the volcanic arc in the solid black line, and those that are further inland behind the line of volcanoes in the dashed black line, because they tend to attenuate more quickly back there. And in comparison to some of the previous ground motion prediction equations that we've had. And you look at a picture like this and you say, oh, this looks great. The motions were all really low compared to the ones that we had before from our prediction equations. And those are, it's a high frequency motion of 5 hertz on the left and a low frequency motion of 0.5 hertz on the right. And so that kind of looks good when you look at it that way, but one of the things that makes it maybe not such a good news story is that the site amplifications that we estimated, while analyzing what were the average motions, we also looked at what are the site amplifications that were actually observed at all these different sites in Japan. And those site amplifications, which have been divided out in the plot that I just showed you to show for a reference condition, those site amplifications were huge. And in particular for some of the higher frequencies, part of that is because of the setting of Japan. Japan is a country where the kind of dominant site setting is a shallow layer overlying rock. And a shallow layer will amplify high-frequency motions. And so there were a lot of stations in Japan that had site amplifications. Here we're looking at site amplifications at different sites as a function of frequency. There were site amplifications for sites in the 5 to 10 hertz range of more than an order of magnitude. And so even though the ground motion prediction equations look low when you look at it for a reference site, for actual particular sites at high frequencies, the motions were very, very, very strong. So this is important not only for understanding the motions that happened in Japan, but also understanding what those motions might look like in BC. We can't simply take the motions from Japan and say, well, let's take motions that happened at 100 kilometers in Japan and see what they looked like, and maybe that's what we'll have in Cascadia, because our site conditions are entirely different. If you look at places like the Fraser Delta, we have these deep soft deposits. So we might be looking at significant amplifications not at high frequencies, but at low frequencies or long periods. So that for us, the problem might be what are the site amplifications and how they might influence high rises as opposed to short period structures. So there's all kinds of things that we're learning from this earthquake, but it's not a trivial matter to apply it to Cascadia. We have to kind of deconvolve the site and the source and the attenuation so that we can then apply the model to Cascadia. And a last thing that I don't think, again, I'm not going to go into here, is that one of the other things we've done for this project, the Canadian Seismic Research Network, is we've developed a number of time histories or acceleration records that one can input to kind of generic studies of how structures behave, and those are also available for engineers on our website. I think I'll stop there. Thank you.